we discussed measures of center and spread. And remember, we mentioned what we're talking about is that data distribution. And that data distribution was our bell curve. And there were two characteristics that were important about it. One was where the center of the curve was. Remember, this is a number line down below here that's being numbered, so we can tell what number that center is above. And the second was the width, or the spread. Obviously, the blue curve and the black curve here have the same center, but the black curve is more spread out. The blue curve is narrower, or less spread, or what we call less dispersion. And for measures of center, we had the mean, which was that average, add them up, divided by how many were there. The median, which was the middle number, half the values were smaller than the median, half the values were larger. The mode, which was the number that occurred most often. And remember, we said that wasn't really useful for numerical data unless we had a really large set, but it's mostly useful for categorical data. Then we had the mid-range, which just used the smallest and largest numbers and found the average, or the number that was in between the smallest and largest numbers, the minimum and maximum. For spread, we had the range, which was just the largest number, maximum, minus the smallest number, the minimum. And we saw that if we had data sets, that was not terribly useful to distinguish. For example, let's do set A here. I'm going to do 17, 21, 24, 25, 27, 31, and 37. The range of set A would be 37 minus 17, which would be a range of 20. 37 was the max, 17 was the min. We subtract to get a difference of 20. If I have set B here, and let's do 17, 18, 19, 25, 32, 34, and 37. The range for set B, well, it's also 37 is the max and 17 is the min. I wrote down 12 here instead of 17. There we go. Giving us a range of 20 again. So those two have the same range, but are they equally spread out? So the tool we used for that, we used a dot plot here. So 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 30, 5, 40. And so let's do set A in blue here. So we have a 17, 21, 24, 25, 27, 31, and 37. Kind of an even spread, kind of almost evenly distributed across the line there. Let's do set B in red. Well, we have 17, 18, 19, 25, 32, 34, 37. Well, they definitely do have the same range, but I would say the red dots are more spread out. They're further away from the center than the blue dots. And that's where we came across this standard deviation or variance calculation. So for set A, let's go ahead and do our standard deviation. So the step one of finding the standard deviation is to find the mean. So for A, 17 plus 21 is 38, plus 24 is 62, plus 25 is 87, plus 27 is 114, plus 31 is 145, plus 37 is 182. There are, what, 1, 2, 3, 4, 5, 6, 7 numbers there, so divided by 7 gives us a mean, I believe, of not 16, 26. 26 there. Step 2 was then subtract the mean from each. So I have my 17, 21, 24, 25, 27, 31, and 37. And from each of those, I'm going to subtract that mean of 26. I'm going to get some negative numbers here. 17 minus 26 is negative 9. 21 minus 26 is negative 5. 24 minus 26 is negative 2. 25 minus 26 is negative 1. 27 minus 26 is positive 1. 31 minus 26 is 5. And 37 minus 26 is 11. Remember, we called these numbers here the deviations, or the deviations from the mean. And if we were to add them up here, they should add up to 0. And in this case, they do. Because on average, the mean is in the middle, so they should be an average distance of 0 from the mean here if we're doing positives and negatives. Because of that, it wouldn't be, if we just add them up, it wouldn't be a very good measure of spread. So we go to the next step, which is to square each number, square each of those deviations. So we have negative 9 squared. Remember, we have to, whenever we square something, we're going to get a positive. So on the calculator, we have to put that in parentheses. Negative 9 squared is 81. Negative 5 squared is 25. Negative 2 squared is 4. Negative 1 squared is 1. Positive 1 squared is 1. 5 squared is 25. And 11 squared is 121. So now we need to add those all up. What do we have? 106, 110, 231, 233. 258 it looks like we have for a total there. If I add all those up, 258. So then step 4 was where we were, what we just did there, is to find the sum. Step 5 is where we have to divide, but remember we divide by n minus 1. And so remember we discussed if it's a sample, which in this class everything we do is going to be a sample, we divide by n minus 1, the number of items in the sample minus 1. If it were a population, we would divide by capital N, the number of items in that whole population. So since this is a sample, we will divide by n minus 1. So n equals 7 here, because there's 7 numbers in the list. So 7 minus 1 is 6. So we divide by 6, which gives us 43, I believe. Let's see what I get here. Calculator. 258 divided by 6 is 43. And so that number, that 43 there, was what we call the variance. In this class, we're not going to use the variance for anything, but if you get into more advanced statistics class, the variance is actually more important than the standard deviation. So step 6 was then to square root it. So the square root of 43 is going to give us 6 point, and square root of 43, 6.56. That's our standard deviation. So here, what this is saying is, on average, these points are about 6.56 units away from the mean, or the center of the data. If we did this for the second data set, and we're going to do this, but I'm going to do it accelerated mode here. I'm going to go into Excel, so it'll do all the calculations for me. So here's my numbers. 17, 18, 19, 25, 32, 34, and 37. So my 7 numbers, I'm going to find the sum here. Add those up, it's 182. I do that divided by 7, gives me a mean of 26. So the mean is still 26, so we're going to subtract the mean. We're going to subtract 26 from each of those numbers. And we'll just fill that down. Next, we're going to square each of those. Let's equal this, oops, not that. This squared. So we squared them all. Then we're going to find the sum of those again. Add them all up. 416. Now this is considerably larger than what we had last time. So divide by n minus 1. So that's going to equal the 416 divided by 6. Give us 69.33. So the square root is going to be 8.32. So that is our standard deviation here. So 8.33 actually is what that would round to 2 decimal places. So if we can compare that to what we had for the last data set, it confirms, if I go back up here to my data set, 6.56. .33. It confirms that that second set B is considerably more spread out than set A is. And so that standard deviation is a great way of describing how spread out that data set is. So next, we've talked about measures of center and spread. We want to talk next about measures of position. And one that many of you have already encountered is percentiles. A percentile is saying what percent of all data is smaller than this. So for example, if you take one of the standardized tests and you test in the 78th percentile, what that is saying is 78% of all scores were less than yours. So that means you tested better than 78% of other people taking that test. That's pretty good. Now, you think a 78th percentile doesn't sound that high, but if you really think about it, the 50th percentile is better than half of the other scores, or of the other numbers, we should say. And if you recall from Friday, the number that's better than half, it's bigger than half the values, it would also be smaller than half the values. The 50 percentile is the actual median of the set of data. It is the middle of the set of data. So if you tested in the 50th percentile, a lot of us think, well, 50th percentile, that's pretty low, that's bad. But it's not. That just means you're average. So that isn't a terrible score. I want to put a set of numbers up here. We're going to do 17, 21, 23, 24, 26, 27, 27, 30, 33, 37, 40, and 45. So there are 12 numbers in this data set. So n equals 12 here for the number of items in this data set. And so we're going to find two things. One, we're going to look at find the number in a given percentile. So to do this, it works a lot like finding the median. Step one is to find the position. Now I should take that back. Step one is technically put the numbers in order, but we already have these numbers in order from smallest to largest, so that is done. Then we'll find the position. So let's say, and then after that, we identify the number in that position. So let's say we're asked to find the 65th percentile. So the 65th percentile, we're going to find that position. N is 12 times 65th percentile as a decimal is 0.65. 12 times 0.65 gives us 7.8. Remember, we said if this is a decimal, we round up. That's the 8th number in the list is going to be our 65th percentile. So let's just number these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, the 8th number in the list is right there, number 30. So 30 is the 65th percentile for that list. Let's find the 25th percentile. So to find the 25th percentile, n is still 12 times 0.25 gives me 3. 12 times 0.25 is 3. Now remember, since this is a whole number, just like we did with the mean, or the median, I should say, it's between that position and the next. So it's between the third and fourth position. So third is 23, fourth is 24. So to find out what's between those, we add them together and divide by 2. So 23 plus 24 divided by 2 is 23.5, is the 25th percentile. Next, let's find the percentile of a number. So the percentile of a number uses a formula. It is the number that are smaller than that number plus 1/2 times the number that are equal to that number over n. Let's take a peek here. Let's find the percentile of 37. If we look up here in our list, here's 37. There are 9 numbers smaller and only 1 equal to it. So 9 smaller plus 1/2 times the one that's equal over, of course, n equals 12. So this is 9.5 over 12. If I divide that out, 9.5 divided by 12 gives us 0.792. We're just going to round that to the 79th percentile. So the 37 here is approximately the 79th percentile. 79% of the data is smaller than 37. Now, I should note, since this is a small data set, 12 numbers seems like a lot when we're calculating by hand here at the early stages. But when you're analyzing data, 12 numbers in a data set is a very small data set. 37 is actually like the 79th through the 83rd or 84th percentile. So there's a little bit of a gray area with our percentiles. If there was a large number, like 400 points in our data set, it would be very, very straightforward. It's exactly this percentile. Let's find the percentile. Of 27. So if I look up here, there's 27. There's 5 numbers smaller, and there's 2 numbers equal to it. So 5 plus 1/2 times 2, 12. Well, 1/2 times 2 is 1, so 5 plus 1 is 6 over 12, which is 0.5. That is the 50th percentile. Remember, we also said the 50th percentile is also the median. So 27 would be the median of this set of data as well. So those are percentiles and how they work. And we've all encountered percentiles in some form through standardized testing or through whether it's just a well-child visits to the doctor saying, yeah, you're in the 63rd percentile for weight and 71st percentile for height and whatever. The percentiles are all around us. In statistics, there's a variation off of percentiles that we use for analyzing a set of data called quartiles. Quartiles split the data, the data points, into 4 equal groups. And by equal groups, I mean each group has the same number of data points in it. Now, if I've got something I need to cut into 4 equal pieces, let's say I just have a piece of wood or whatever, and I want to cut it into 4 equal pieces. I only need to make 3 cuts to get 4 pieces. So there are only 3 quartiles because it only takes 3 quartiles to cut our data into 4 equal pieces. Quartile 1, sometimes called the lower quartile, and abbreviated as just capital Q1, is the 25th percentile of the data. So up here, we did the 25th percentile is 23.5 for this set of data. Quartile 2, almost never called quartile 2 because it is just the median for the 50th percentile. And we saw that up above, that is the 27. Oh. And quartile 3. Sometimes called the upper quartile because at the upper end of the data. Abbreviated just Q3, is going to be the 75th percentile. Now, we haven't calculated this yet, so let's find the 75th percentile up here. So it'll be 12 times 0.75, which is 9. Since that's a whole number, that means it's between the 9th and 10th number. So the 9th number up here is 33. The 10th number is 37. Between 33 and 37, 33 plus 37 divided by 2 is going to give us 35. So there we have our quartiles for that data set. Now, these quartiles are important in themselves because they give us another measure of spread called the interquartile range. From here on out, just abbreviated IQR. And the interquartile range is the third quartile minus the first quartile. The Q3 minus Q1. So here that would be 35 minus 23.5, or 11.5. Well, why is that important? Well, because we can compare it to the full range. So the full range of this data, it goes from, where was it here? 17 to 45. So 45 minus 17 would give us the range. It should be 28. So we have an interquartile range of 11.5 and a full range of 28. So the interquartile range contains the center half of the data. The full range, of course, contains all of the data. Now you might say, well, shouldn't that be about half? Well, that would be a logical conclusion, but remember, most of our data is packed tighter in the middle of the distribution. That's why we have the bell curve. So having the interquartile range less than half of the full range is a good indicator that this might be a normally distributed set of data. If the interquartile range were more than half of the full range, well, then it's definitely not a normally distributed set of data. And so there's a tool we use called a box plot. Some textbooks refer to it as a box and whisker plot. And what this does is it displays the 3 quartiles and also something called the 5-number summary. And the 5-number summary includes the quartiles along with the smallest number, the minimum, Q1, the median, or Q2, Q3, and then, of course, the maximum, the largest number. So for our data set up there, the smallest number was 17, largest number was 45. 23.5 was the first quartile, 35 was the third quartile, and the median was, where'd it go, 27. And so to make our box plot here, we start out with a number line that gives us the full range of the data. So we'll start out at something less than 17. We'll start out at 15. And we have to make sure we go all the way up to 37 here. So what we're going to do, we're going to mark the minimum and the maximum with dots. So 17 is a dot. 45. Oops, I got to get up to 45 yet. Then there's a little bit. So 45 for the maximum. There's a dot for the maximum. The quartiles and the median then get marked with vertical lines. So 23.5 for the first quartile, 27 for the median, and 35 for the third quartile. Then we connect the first quartile to the third quartile, like that, to make the box. Notice we have the box with that little hash mark in the middle where the median is. Then the whiskers extend from the quartiles out to the minimum and the maximum. So there's our box plot, or box and whisker plot. The smaller the section of the box and whisker plot, the more tightly packed the numbers are at that section. There's 4 sections, 1, 2, 3, 4. Now this is the largest section here, so we would say that's where the numbers are the most spread out. This is the smallest section here, so we'd say that's where the numbers are the tightest together. And let's just plot our numbers in the dot plot superimposed over the box plot to display that. So we had 17, come on. 17, 21, 23, 24, 26, 27, 27, 30, 33, 37, and 40, 45. So you can see, yeah, they are very tightly packed together here, very spread out over here. So the box and whisker plot does accurately display the distribution of our data. The dot plot is more precise because it gives you every individual data point, but the box plot is often a quicker reference. So we mentioned normally distributed earlier. And we had mentioned that because the interquartile range was less than half of the range, that was a good indicator that this could be normally distributed. Well, a box plot for perfectly normally distributed data, first of all, would have the median exactly in the middle of the box. Then the whiskers, longer than each of the sections of the box. So our plot up here is a little bit skewed. It's stretched out a little bit more on this side. Both this section and this section are stretched out more than the 2 sections over here, but it's relatively close. So you might be able to say that that's pretty close to being normally distributed, although obviously not perfectly normally distributed because it's not symmetrical. So these normally distributed set of data are huge to us in statistical analysis because most populations produce data that are normally distributed. Because of that, we have a lot of different ways of breaking down normally distributed data. So if we go back to that bell curve, this bell curve has some very specific properties that are very useful for us for breaking down data and how likely it is for data to take on certain values. We use something called the empirical rule. Uses the center of the curve and the standard deviation. Now, for center, we could use the mean or the median, even the mode if we have enough data points to have an accurate mode. Because we use the mean to calculate the standard deviation, we're going to use the mean for our center here. Again, the median should give us the same value. And remember, the mean will be at the very center of this curve. That's our mean. And what we found with normally distributed sets of data, the standard deviation describes a specific percent of the data points for every set of normally distributed set of data. So what I mean by that, well, if I go from the mean and I go out 1 standard deviation to the side, each side. So let's go out 1 standard deviation here. And 1 standard deviation here. So this would be plus 1 standard deviation. It's the mean plus 1 standard deviation. This would be minus 1 standard deviation. Let's put some numbers to this so maybe it makes a little more sense. Let's say we have if we're looking at the cost of x-rays. We did a sample of different clinics in the area. We found that the mean cost is $450 with a standard deviation of $60. So that means the center of this curve here is 450. Adding 60 to that would make this 510. Subtracting 60 from that would be 390. So because we have a mean of 450 and a standard deviation of 600, or of 60, we get a range, one standard deviation around the mean that goes from 390 to 510. And the empirical rule tells us that we expect 68.3% of all the data points to be within there. So let's say for our sample, n equals 500 clinics. 500 times 68.3%, the calculator for speed, is 341.5. We're going to expect 341 or 342 of those clinics to have x-rays that cost between 390 and 510. So if we go out then 2 standard deviations, those would be plus 2 standard deviations. I'm just going to use SD instead of STD. Or 2 standard deviations below, so this would be minus 2 standard deviations. Again, the prices that would actually go on there, so 450 plus 60 was 510, plus another 60 is 570. 450 minus 60 was 390, minus another 60 is $330. So that range, 2 standard deviations around the mean, goes from $330 to $570. And the empirical rule tells us we expect 95.5% of all the data to be in that range. So over 500 clinics, we expect 477.5. So 477 or 478 of them would be between $330 and $570 for x-rays. And of course, we can go one more, plus 3 standard deviations, minus 3 standard deviations. So that would be, 450 plus 60 plus 60 plus another 60 would be 630. Subtracting 60 gives me 390, 330, another 60 down would be $270. And the empirical rule tells us that the percentage there is 99.7%. Fall within 3 standard deviations of the mean. So we're saying that of those 500 clinics, 99.7% or 498.5. So 498 or 499 of them would be between $270 and $630 for x-rays. So only 1 or 2 clinics would be outside of that range. And statistically, they say 1 would be less, 1 would be more than that range. So if you go to a clinic and that clinic is going to charge you $550 for an x-ray. Well, $550, that's somewhere in here. That's telling you that's more than quite a few of the other clinics in the area. They're charging you a lot for that x-ray. In fact, let's take a look at an example that helps us break down what to do with these percents. Let's say you're looking to buy a house. And so you want to buy a 3-bedroom, 2-bathroom house. And you do your research in the area you're looking in last year, of all the homes that sold that are 3-bedroom, 2-bathroom, the mean selling price was $230,000 with a standard deviation of 60,000. So what that means is if we're looking at our bell curve, center of this bell curve is going to be 230,000. We go one standard deviation to each side. We add 60,000 to get 290,000. Subtract 60,000 to get 170,000. We're expecting 68.3% of all homes sold to be within that range. Go to another standard deviation here. Plus another 60 would be 350,000. Minus another 60 would be 110,000. We're expecting 95.5% of all those 3-bedroom, 2-bathroom houses to have sold between that range. And going on a third standard deviation each side, so plus another 60, this would be 410. Minus another 60 down here, this would be 50,000. 99.7% are going to be in that range. So let's say then we find a house that we really like and its price is $350,000. And your real estate agent is saying, well, you better put in an offer on that right now or it's going to be gone. In fact, you better put in an offer that's more than the selling price. Well, if you look at what's going on here, so this cutoff right here, this is 95.5%. If 95.5% is between these two blue lines, that means 4.5%, 100 minus 95.5 is 4.5%, 4.5%, is outside of that range. And since this is symmetrical, that's split 2.25, 2.25% to each side. So 2.25% of houses fall in this range and 2.25% fall down here. So in other words, only 2.25% of 3-bedroom, 2-bathroom houses in that area have sold for more than $350,000. And looking at the other side of it, 100 minus 2.25%, 97.75% of 3-bedroom, 2-bathroom houses that have sold in that area have sold for less than that amount. So chances are you're going to find another house that you like that's cheaper than the one that you were looking at. Okay, so with that, we'll give you some homework here. Your homework, you're going to have page 353 through 354. 1 through 7 there. And page 357 through 358. 1 through 6 there. That, you guys have a great day, and hopefully we'll see you all back here on Wednesday. By the way, next week, Wednesday will be our test, so make sure you're prepared for that. Thanks. You guys have a good day.